familiar here. Squaring a number and taking the square root of the results are similar to inverse operations. So a square root and a square, or a radical and an exponent, are really inverses of each other. They undo what you did. So if I were to say 3 squared equals 9, then the square root of 9 equals 3. That's how we're going to go back and forth. You'll notice that it said the square roots of 9 are 3 and negative 3. You really only consider this negative piece when you're talking about variables. Typically, if they just say, hey, what's the square root of 9? You're going to say 3. But if you say x squared equals 9, then you would say x could be 3 or negative 3. And so that's what we're going to look at when we start throwing variables in here, is that you have to consider the positive and negative roots sometimes. So let's look at this first example. Example 1 here tells us that we need to find the root. So let's talk a little bit about what the symbols mean. In example 1, we just see a square root. The square root symbol is what you are familiar with. So this square root here is what you're familiar with. This is called the radical sign. So when I say under the radical or outside the radical, I mean that sign right there. If it doesn't have a number here, then you are talking about the square root. The actual number here is called the index. And if you don't see one, it is automatically assumed a 2. And so just like when we did bell work and it said the square root of 16, it didn't tell you there was a 2 there, but you automatically know that you're looking for something that multiplies twice. You can have other size roots. So you can have a cubed root, and you're going to have a little number here that tells you what root you're looking for. If 2 cubed equals 8, then the cubed root of 8 is 2. You are saying what number multiplies 3 times to get to 8. That's 2 times 2 times 2. All right? Nth root. This just means this could keep going. We could say the 4th root, the 5th root, the 6th root. We could look for any number of roots, and that little number tells you what root you're looking for. So we start with square roots. These are what we're familiar with. The square root of 4. We're just looking for what multiplies twice to get to 4. That's going to be 2. These are ones that we know. This one wants the square root of 16, and then we have a negative in front. Think of order of operations. The radical is like a grouping symbol, and the negative one is in front multiplying it. So you're actually going to take the root first, which is a 4. Square root of 16 is 4. And then you're going to apply that negative 4. All right, and so that's what it looks like when there's a negative on the outside of the radical. Higher roots, let's look at example 2. All right, so in example 2, they want us to find higher roots. This first one, they want the cubed root of 125. And so we need to find something that multiplies 3 times by itself. Now here's the thing, some of these you're going to know, but when you don't, you can use a factor tree, okay? So factor tree is something that we've talked about a little bit before. We're going to talk about it even more now. Factor tree is something that you probably did long ago when you were doing primes. You're going to split it up. You're just dividing. And so I always start with a prime on the left. I'm going to say what prime number goes into 125, and that is 5. And then all you do is divide 125 by 5, and you're going to get 25. We're not done yet because 25 is not prime, so we're going to split it up even more. 5 goes into 25 5 times. And now you can see that all of my numbers here are primes, right? You can also see what my cubed root of 125 is. The number that you multiply 3 times to get 125 is going to be 5. 5 times 5 times 5 equals 125, which means the cubed root then of 125 is 5. What number multiplies 3 times 5 to get 125? That's what we're asking for here. Let's look at 81. 81, again, it might be something you know intuitively, but we're now looking for something that multiplies by itself 4 times to get 81. And so if you don't know a prime that goes into it, hopefully you know at least 2 numbers that go into it that look like this, right? We're not done yet though, because those are not primes. So we're going to split it up, each one of those. And now we've got primes. You can see we have 1, 2, 3, 4. If you multiply those, you would get 81. The 4th root of 81 then is 3. And that's all higher roots mean. They're just telling you, hey, it has to multiply by itself this many times. That's what I'm looking for. All right. A negative inside a radical does not necessarily mean we have a problem. So, there are times when negatives are okay in a radical. There are times when negatives are not okay inside of a radical. And so what you're going to look for is you're going to look for that index. All right. If your index is even, so if we have an even index, you cannot have a negative inside the radical if we're talking about real numbers, which all of these for now are real numbers, okay? If it is odd, then it's okay to have a negative inside the radical, all right? Why is that? Well, if I multiply any number by itself an even number of times, it should be positive, right? Because a negative times a negative is a positive. And so every time I do that in groups of 2, I should get a positive. If I have a cubed root or a fifth root or a seventh root, that means I have an odd number of times that I'm multiplying it. So it's okay if I have a negative. It just means my answer will be negative. -1 times -1, well, that's positive. But -1 times -1 times -1, that's negative. So an index that is odd, you can have a positive or a negative inside. That just tells you what your answer will be. If you have an even index and you have a negative on the inside, your answer is no real number. We do not have a real solution here. And we'll get to imaginary numbers later on in math life. But right now we're talking about real numbers. And so if I said real numbers here and I look at these groups, square root of -4. Well, I can have a square root of +4, but the index, when you don't see one, is 2, which means this will not have a real number answer. So there is no real number that you can answer that question with. In real numbers, this would be the empty set. You do not have a number that answers that question in a real number form. Let's look at the next one. -27 over 125. My index is odd. I need a number that multiplies 3 times to get this. It's going to be negative. For a fraction, just do the numerator and the denominator. So what number multiplies 3 times to give me 27? 3 does. What number, we just found it, multiplies 3 times to give me 125? It's 5. And because I need my answer to be negative, this is going to be negative. And so this is going to be the cubed root of -27 over 125. And you can check it. If you said -3/5 times -3/5 times -3/5, negative times negative times negative is going to give me a negative answer. 3 times 3 times 3 is 27. 5 times 5 times 5 is 125. So this is the correct answer. Questions on that? Let's look at 32. So 32 you may not know off the top of your head. The first thing you want to decide is, can I do it? Fifth root with a negative on the inside, can I do it? Yes, it's odd. Now you just have to figure out what number does it 5 times. If you don't know, use your factor tree. 2 and 16, 2 and 8. You probably see a pattern here, right? So what number multiplies itself 5 times to get to 32? 2 does, and specifically because this is -32, my answer is -2. So if you look here, it says knowing a perfect square will help you determine things. And really, if you practice, you're going to recognize even like 13 and 14, 15's an easy square. Really up to about 20 is good ones to just know, because then you start recognizing them. But some of the things you want to start keeping in mind is you have radicals that are not going to be a perfect number. So if you were to use a calculator for something like the square root of 7, it's going to be an irrational number. We talked about number sets like first day, I think, the first section of this book. irrational numbers. And one of the examples of irrational numbers are square roots that don't have a perfect square. Those decimals go on infinitely. So for me to ask you what the answer is, unless you're a calculator, you're not going to be able to tell me. But you should start seeing patterns. Like if I want the square root of 7, logic tells me it's going to be in between two perfect roots on either side of it. Well, the closest perfect root on the low end of 7 would be a 4, right? 4 squared, or 2 squared would be 4. And then above it would be 9, square root of 9. So square root of 4 and square root of 9 are the two perfect squares that kind of bookend square root of 7. So I know that if the square root of 4 is 2 and the square root of 9 is 3, then the square root of 7 should be somewhere in between 2 and 3. And that's going to help me like when I'm graphing or when I'm doing different things, when I'm estimating, then I could say, okay, I may not have a perfect root, but I know I'm somewhere between 2 and 3. And you can estimate it that way. And so that's what they do with estimating roots. And I'm not going to have you do huge ones. But you do want to think about if you had something like the square root of 129, which is what they have here. Then you want to think about two roots that are on either side of it. Hopefully you know 11 squared, which is 121, right? So square root of 121 should be somewhere probably on the left-hand side. And then 11, 12, that's 144, right? And so I know that 129 falls between these two numbers, which are perfect squares. So I know the answer to this is going to be somewhere between 11 and 12. And so it just helps you get in your mind what a good estimation would be for averaging these in between them. All right, because you're not always going to have a perfect square. Everybody's favorite. So you can have any type really of exponent. You're used to x squared, x cubed, those nice pretty integers as your exponents. We introduce negative exponents. That puts them in the denominator. You can also have fractional exponents, okay? Fractional exponents are actually just radicals written in exponential form. So let's look at what it's telling us here. The expression x to the AB is the same thing as this radical, all right? The numerator of your exponent, the numerator of this little fractional exponent, you notice was the exponent of whatever's inside the radical. The denominator of my fraction became my index. And they give us an example here. 8 to the 2/3. All right? That is the cubed root, 3 became my index, of 8 squared. All right? You can do this two different ways. You can square it first and then take the radical, or you can take the radical first and then square it. Typically, it's easier to do this one first because you have a smaller number. So if I do it this way, I'm going to say 8 squared is 64. The cubed root of 64 is 4. All right? If I do it this way, the cubed root of 8 is 2. 2 squared is 4. These are the same thing. They're just written two different ways. And so when you see a fractional exponent, it is just a radical. That's all that is. It is just a radical. And so the first thing we're going to do is we're going to rewrite them. All right? It says convert 5 2/3 to radical form. So they gave it to us in exponent form. They want it in radical form. So if I want to change this to radical form, I'm going to do a radical. This denominator is my index. On the inside, I'm going to have 5 squared. Or you can write it this way, the cubed root of 5 and the whole thing squared. That is rewritten. So if I want to write the next one, they gave it to me in radical form, and we need to rewrite it to exponential form. So if I rewrite that one to exponential form, it's going to be x. This 3 is my numerator. This 5 is my denominator. X to the 3/5. Questions on rewriting? All right, it does not matter how many things are in it. So if you look at this right here, one of the things it's asking me to do is rewrite it as a single radical. The only way to write it as a single radical is to have the common denominator. So we are going to have to pull back in our memory as to how to get common denominators here. So what's the common denominator between 1/2 and 3/4? Yeah, it's 4. So I can actually rewrite this one right here to be 3 to the 2/4. and x to the 3/4. All right, how does that help me? Well, I can put them under one radical now. So I can rewrite this whole group. Radical, my index now is the same, it's 4. I can say 3 squared x cubed. And you can simplify that. My 3 squared is just 9. So that's the 4th root of 9x cubed. All right. If they want me to convert the other way with multiple things on the inside, you just take each piece. Think about the exponent on 7. If you don't see an exponent, it's 1. So I would say that's 7 to the 1/4. Then I'm going to do my x to the 3/4. Then my y to the 2/4. You think there's anything else I'm going to do for this one? Yeah, I'm going to reduce it if I can. And so I can reduce this piece of it. So it's going to be 7 to the 1/4, x to the 3/4, and y to the 1/2. And that would be converting it the other direction. So if I don't see an index, my index is going to be a 2. If I do not see an exponent, my exponent is going to be a 1, and that includes your whole numbers in there. It includes your integers. And then I'm just going to rewrite it. My 3 is my base. This is my exponent, which is why that went there. This is my denominator, so that's my index. That's why it went there. Same thing with the x. This is my numerator on my x, denominator on my x. So for 35, you want to see that they have the same denominator, which means they can go under the same root. So since they both had a 2, remember your index is 2. Denominator represents the index of the root. That's why that's the square root. And then they were both to the first power, so we just had to list both of them under the same root. As long as they have the same index, they can go under the same root.
So you don't have to write the 2?
Number 39, you would have gotten a common denominator first. My common denominator here is going to be 8. So that already has my common denominator. R, to make that an 8, it would be 2 over 8. S, to make that an 8, I would multiply by 4, 4 over 8. And then once they all have the same denominator, they can go in the same radical. And then I just have 3 cubed, R squared, and S to the 4th, all in the radical with an 8. And then I just simplified that 3 cubed. All right, so this first thing's kind of important. You're going to use this a lot. As long as x and y are greater than or equal to 0, if you have the same index with an x and a y under the index, it's the same thing as splitting them up, and vice versa. So what this means is if you are multiplying radicals, as long as they have the same index, you can just multiply what is inside. All right? So you can just multiply what's inside as long as they have the same index, or you can split them up if they have the same index. So to simplify radicals, you need to write the radicand as the product of its prime factors, apply the product's property, simplify the roots, and multiply the factors outside. So there are going to be times when you recognize this a little bit easier than others, and I teach it a little bit differently than they do. So we're going to do factor trees to do ours, because I don't think you always recognize the perfect root. Simplify 24. All right, so prior to this, we've been given perfect roots. Does 24 have a perfect root is the first question. It does not. So then I'm going to look at the index. What is the index on this radical? It's a 2, all right? So when I do this simplification, I'm going to use a factor tree, and I'm going to say, all right, I'm going to break this up into all primes. I try to put my primes on the left-hand side so they don't get caught up in my factor tree. So like I would start with a 2 here, and I would say 2 times what is 24, or 24 divided by 2, whichever way you look at it, and that's going to be 12, right? And then I'm going to keep going. 12 can be divided as well to 2 and to 6. And then 6 can be divided 2 and 3. All right? If my index is 2, then anything that groups by 2s can come out of my radical. All right? And so I'm going to say, well, this is a group of 2, right? There's 2 of those. 1, 2. So a 2 can come out, right? However, this only has 1 now. You can't group with anything. This cannot group with anything. Neither one of those can come out of my radical. They have to stay inside my radical. When more than one thing stays out, or when more than one thing stays in, you just multiply them. So my final answer here is going to be 2 square root of 6. And that is my answer. All right? So I'm going to do the same thing with 75. What's an easy number that you automatically know goes into 75? 5, all right? And so I'm going to say 5, and I'm going to divide this, all right? What is 75 divided by 5? 15, all right? 15, well, that can be broken up in 5 and 3. What is my index up here? If I don't see one, it is a 2. So anything that pairs up in 2s can come out of my radical. That means there's 2 of these. Since there's 2 of them, it can come out of my radical. Does this one have a pair? It does not. So it has to stay inside my radical. So if I simplified this square root of 75, that's the same thing as 5 times the square root of 3. The reason that works, let's just look at why that works. 25 times 3. Does everybody agree that is 75? All right. We just said that if we have 2 radicals, we can just multiply them, right? What is the square root of 25?
5.
So this is 5 times the square root of 3, which is what we got. Does everybody see that? All right, let's look at the next one. 40. What's my index on this one? 3. So I'm no longer looking for something that groups in 2s. I am now looking for something that groups in 3s. And so I'm going to do exactly the same thing that I did. What goes into 40? What's a prime that goes into 40? Easy. If it's an even number, it's a 2. So 2 times what equals 40? 20. I can use 2 again, right? 2 and 10. 2 and 5. Those are all primes. I'm done. Now I need to group it in 3s, right? I need to group it in 3s. So I'm going to say 1, 2, 3. That is a group. It meets that criteria. It can come out. 5 does not have 2 more that goes with it. It has to stay inside. I have to make sure that I use that index when I do this. All right. If it's anything but a 2, you've got to write your index there. And why does this work? Well, 2 times 2 times 2, that is 8 times 5. Everybody agree that's 40? 8 times 5? Cubed root of 8 times the cubed root of 5. What is the cubed root of 8? 2, right? 2 cubed root of 5, which is exactly what we got here when we used our factor tree. All right, so you've got to be familiar with breaking things up into primes. 648, because, you know, I want to spend all day factoring. All right, it ends in 8. What do you automatically know goes into it? Small prime. Yeah, so we want to use it. 4 will go into this actually, probably, maybe. But we want to use a prime so that we don't get lost in there. If you absolutely can't tell a prime, you can use a bigger one. Just make sure you don't lose. What happens when you start doing a factor tree is you'll lose them in the midst of it, and you'll forget one of them. So I always try to keep my primes on the left side. So if I start with 2, just divide each number. 6 divided by 2 is 3. 4 divided by 2 is 2. 8 divided by 2 is 4. Right? And you can just keep going. 2 goes into it again, right? So 3 divided by 2 is 1 with 1 left over. 12 divided by 2, just do it like this so you take your time. We're going to get to where 2 doesn't go into it in just a second. So right here. We are out of 2's, right? What goes into 81? Yeah, so I'm going to start actually with 3 just so I don't get lost in it. 8 divided by 3 is 2, right? With 2 left over. 21 divided by 3. And we can just keep going here. All right, what's my index? What's my index on my radical? 2. So I need to look for things that group up in pairs. You'll notice that I have a pattern here of how I'm doing this. I circle the ones that group. 2 and 2, that's a group, right? This no longer has another one to go with it. So I box that one. 3 and 3, that is a group. Another 3 and 3, that's another group, okay? So I can pull out a 2. I can pull out a 3. And I can pull out another 3, all right? On the inside, I have this 2 right here, just like that. To simplify it, multiply everything that got taken out, multiply everything that stayed in. So 2 times 3 is 18, and then I have a 2 on the inside. So that's how you do larger numbers, right? You're just looking for things that group according to what your index tells you how they have to group, all right? And when I do my factor tree, I'm just using a small number and dividing it by that small number, and then I'm just breaking each one down until I'm all primes. And once you're all primes, circle the ones that group, box the ones that stay in. That's my method. You don't have to do it, but that's my method so that I don't forget any of my numbers that I have in that factor tree. When you have a number and variables, you just do them individually. So I'm going to take this 32 and I'm going to do my factor tree with that. And I'm just going to break it up just like I've done every other factor tree. All right. For my variables, there's 2 ways to do this. I'm going to show you both. The first way is just to list it out. If I have x cubed, that is x times x times x. That's 3 of them. If I have y squared, that is just y times y, all right? That's fine and dandy when it's 3 and 2, right? If it were to like y to the 12th, I don't want to write it 12 times personally. So I'm going to show you both ways that I do this for variables. The first way is I can treat it just like I do my numbers. For the numbers, I would say, oh, well, here's a pair because my index is 2. Here's another pair, and then that one stays. So for my numbers, I have 2 times 2 on the outside, and I have one of my 2's on the inside. I can do that exact same method for my variables. I can say, oh, well, let's look at my x's. For my x's, I have a pair here, and I have one that doesn't group. So that means I can pull an x out here, and I leave an x on the inside. And I can do the same thing with my y's. I can say I have a group of y's, and nothing stays in. So one of my y's, there we go. All right, so I can do that method as well. The other method is to take your index and divide him, or take your exponent and divide by your index. So I have x cubed, I would say 3 divided by 2. That is 1 with the remainder of 1. Everybody agree? This tells you what comes out. This tells you what stays in. All right? If you look at y's, I have an exponent of 2, and I'm dividing by that index of 2. 2 divided by 2, well, that is 1 with the remainder of 0. I had 1 y come out and 0 y's stay in. That will always work for your exponents of your variables. You can just divide. The divided by number, the whole number, is what stays out. The remainder is what stays in. Okay, that's how many you take out, how many stays in. Or you're free to list them and circle them just like you do your factor tree. It will work both ways. So once I do this, I group it by my index. Whatever comes out, out. Whatever stays in. So I have a 2 on the outside. I have a 2 on the inside. For these, I have x squared. So if I use this method, 2 divided by 3, that's going to be 0 with the remainder of 2, right? If I were to list them, that is x times x. Nothing groups up 3 times, so both x's stay in. So for this, I have 2 x's that stayed in. Let's look at my y. This is y to the 4th. If I divide it, 4 divided by that index of 3, 1 with the remainder of 1. I'm going to have 1y that comes out, 1y that stays in. And then look at my z's. To the 6, 6 divided by 3. That is 2 with the remainder of 0. That means 2 of my z's come out, none of my z's stay in. Make sense? We had a 5 that came out. 1 of your A's came out. None of your B's came out. And 4 of your C's came out. So we have 5A, C to the 4th. On the inside of this radical, we had a 3 that stayed in, which is where we got that. 1 of our A's stayed in, which is where we got this. And 1 of our B's stayed in, which is where we got that. None of our C's stayed inside.